All right, just a little bit of a summary of what we learned. So we learned different types of alpha halogenation. We learned them under acidic conditions. This one's the most useful. So for example, here we would just add aqueous water and some bromine. And then we will get monohalogenation at that alpha position. Upon the addition of a base, usually pyridine, but if you have multiple beta hydrogens compared to this bromine, you can think about using a bulky or non-bulky base to insert that alkene where you want it to go. In this case, we just have one, so we don't have to worry about it. We can form our alpha beta unsaturated compounds. We can also do this reaction under basic conditions, but it's not as useful. And it's not as useful when we get multi-halogenation or polyhalogenation. So for example, if we had this compound and then we added some sodium hydroxide and then Br2 and then just do an aqueous acidic workup, we would actually take it all the way to the carboxylic acid. And before it gets to the carboxylic acid, it would have 3 bromines attached to it. And then finally, that's a decent leaving group. And then it leaves and gets turned into a carboxylic acid. And then finally, for the alpha halogenation, we learned the Halogenation-Walhart-Zielinski reaction as well. This one's not that useful either. What this reaction allows us to do is it allows us to monobrominate the alpha position of a carboxylic acid. So you can see we've added a bromine there. So there are alpha halogenations, but of course we've learned other reactions as well. We've learned the aldol addition and condensation reaction. So for example, when we have a carbonyl, we just add some base to it. And then it's just going to react with itself in an aldol addition reaction. And then that gives us our beta hydroxy ketone or aldehyde. And then if we heat this, we can get our condensation reaction to form our alpha beta unsaturated carbonyl. We also learned the Claisen reaction, which is basically just an aldol with an ester instead. Right, so now instead of having an aldehyde or a ketone, we now have an ester. That's the same thing, we just add some base. And then here we have to do an aqueous workup. Note that the base that you use, it's always some kind of ethoxide, and your OR should match whatever you have here. And then we end up with the condensation with itself. Note that here we end up with 2 carbonyls as opposed to a carbonyl and an alcohol or alkene because we have this good or decent leaving group over here. So think about the mechanism there. Another useful reaction we learned was alkylation of that alpha position via the enolate. So for example, if you have an asymmetrical carbonyl, like this one right here, we can pick which side to alkylate. If we want the more substituted position, we use a less bulky base, and we do that at a higher temperature, usually room temperature. And then you just add your electrophile. And then this electrophile or this haloalkane will get added into the more substituted position. If you want to add it to the less substituted position, we use the bulky base or LDA. We do it at colder temperatures, so negative 78 degrees Celsius. And then you add your alkyl halide, and now it'll add to the less substituted position. We learned the malonic ester synthesis, right, where we just have this malonic ester. Remember, this one doesn't need a strong base because it has that doubly deprotonated or doubly conjugated anion. And here we can add up to 2 R groups, right? If you want to add another R group, you just add another string of base followed by your alkyl halide. And then we do the aqueous workup to turn our ester into a carboxylic acid, and then we heat to do the decarboxylation. And what we end up with is a carboxylic acid with 2 R groups on it, right? Where the R groups came from those steps right there. We can do essentially the same reaction, but if we don't want to end up with a carboxylic acid, we want to end up with something else. We do that with the acetic ester synthesis, where we use essentially the same reagent above, except instead of having 2 esters, we're only going to have 1 ester. And then we do the same reactions, right? Those dots mean same reaction. Right. And now, instead of having a carboxylic acid there, you've got some kind of carbonyl. And then finally, we'll learn the Michael addition. And for this one, we want to use our alpha beta unsaturated carbonyls that we've seen how to make previously. So we can do different things with that. If we just want to add R groups to it, we can just use a weaker nucleophile, such as our Gilman reagent, and then aqueous workup to return to our carbonyl. We can also use this compound right here, which will have that doubly conjugated anion. So we can just use a weaker base, something like potassium hydroxide. Then add our alpha beta unsaturated compound, and then do an aqueous workup. Right, and then think about where your bonds are going to be formed. It's going to attack at that 1 position. So we'll add 3 carbons here. If we don't have some doubly resonance stabilized enolate, what we can do is the enamine synthesis instead. So for example, this one right here, this would not work with the reaction up above because this, if you try to form the enolate here, it would be too strongly basic and it would attack, it would do direct addition versus conjugate addition. And so what we do here instead is add our enamine reagent, right? We're going to add that one. It's going to form the enamine. After it's formed the enamine, then it can do the conjugate addition. And of course, hydrolyze at the end. All right, we're going to attack that 1 position, right? 1, 2, 3. One, two, three, right there. Note that our carbonyls, we end up with 2 of them, and they are in the 1 and the 5 position relative to one another.